here. We started yesterday by discussing discrete time systems and paid some attention to a particular form that the discrete time system would be expressed in, and that was something called a difference equation. So we ended up on what we did yesterday. We made this little comparison that the continuous time systems, we know that, are described by differential equations, and you solve them, those differential equations, by any number of techniques that you have learned in mathematics, and some which you wouldn't have learned at all. But basically, they involve series solutions or direct integration and other techniques. In our case, our predominant or preferential way in our program for solving differential equations is to use a Laplace transform. And of course, once you get the solution now, that allows us to use to convert the answer now back into things like resistors and capacitors and op amps and the like. All right. So we have that part, and then we saw that in the case of discrete time systems, the discrete time systems basically are numbers, right? They operate on numbers, numerical values, however they happen to be stored. And what describes the behavior of a discrete time system is something called a difference equation, right? And the solution is a sequence of values which gives the response of the system that you're looking for. And you can solve the difference equation by using something called recursion, which works in all of the simplest forms. But usually when it gets more tedious, then you have to resort to something else. The tools that we had before wouldn't work. The Laplace transform does not work well with sample signals, right? In fact, when you try to work the Laplace transform with sample signals, what you get are answers that have an infinite number of poles. You remember in our normal continuous time system, if you have something like S plus A over S squared plus BS plus C, for argument's sake, something like this is going to have 1, 0, and 2 poles. If you convert this in some form, and we're not talking about that here, but if you were to convert this into some discrete time version and try to apply the Laplace transform for it, you remember what sampling does, right? Sampling, early on we said sampling is when you take a signal and you multiply it by an impulse train. And what happens is that the impulse train picks out the value of the signal at each of the point of the impulse train. Well, what happens is that when you apply these sample signals, because of the nature of the impulse train, the Laplace transform starts to create poles that were not there before. And you get this repetition being created, and you end up being more complex than you ended up than you were in the first place. So what we need is something different. And this different thing is something called the Z transform, right? And this is what we're going to spend today talking about. So if you have a discrete signal, right, and we represent the discrete signal as xkt, and xkt may be a set of values. So xkt, right, could be a series of values like 1, 0, 7, minus 5, 14.6, etc. Right? You don't know. It could be any set of values inside of here. They can be all real numbers, right? And exponents and so on. Any set of numbers that you may like. At this point, we're not considering imaginary numbers here for our purposes here. Right? So any set of real numbers inside of here could be xkt. The discrete time, a discrete signal xkt has a Z transform, and we're going to call it x of some function z, right? Just like how the Laplace transform of x at t give you xs, the Fourier transform give you xj omega, right? The Z transform is going to give me something xz, a function of z. Z is a complex variable, which is not unusual. in the Laplace domain, you remember S is a complex variable. It has a real and an imaginary part. So Z is complex. Nothing strange about that. And the way you calculate the Z transform is from this expression here, that xz is a sum from k equal minus infinity to infinity of xkt, whatever the values of that are, z to the minus k. All right, so look at that there a little bit, and we're going to expand on that in a second. Now, just a note, the Z transform, this is just an aside, you don't really have to know this, but just for information, is actually something that comes from the Fourier transform. And if you think about it, the Fourier transform and the Fourier series are great at handling things that repeat periodically, especially the Fourier series. When you sample signals, you get repetition being created, and the Laplace transform can't handle it, but the Fourier transform is made for that sort of thing. So a version of it is what we now have here as the Z transform, right? Specifically, there are two flavors of the Z transform, if you like. The one that sums from minus infinity to infinity is called the two-sided Z transform, because it's running from k equal to minus a huge number to k equal plus a huge number. Or if k sums from 0, then we have the one-sided Z transform. Most of the cases that we will use the one-sided transform. But because we have a situation that we mentioned yesterday, that discrete time systems can be non-causal. In other words, have values before 0, then to handle that, we need a two-sided version, which k will take into account values of t before 0, right? The answer is a complex quantity, and it is a power series in negative powers of z, right? So if you expand this, this is simply, look at the one-sided version. If I just plug in values, look how simple the transform is. K equal to naught means x0, z to the naught, which of course is 1. K equal to 1 is z xt times z minus 1. K equal to 2 is x2t by z minus 2. So for instance, if I had that xkt was equal to three numbers, 1, 9, and minus 8, right? The Z transform of that, right? K equal to naught, so the Z transform of this would be x0, which is 1, z to the naught, which is 1, so 1 by 1 is 1, plus 9, z to the minus 1, minus 8, z to the minus 2, right? So x, z would be equal to that. As simple as that. Yeah? Look easy? Kind of easier than that, right? Good. No integration or anything. You're expanding. Sometimes if you go to the textbooks, you sometimes see this expressed in this form, right? They put it there, and then they have the answer x0 plus xt over z plus x2t. Just now, I'll get back to that in a second. I forgot what I had up. Over z squared plus, in other words, some mathematics books, for instance, put this as 1 over z. Right. Just let me write out 1, 9, minus 8. Hold on to that. Some of the mathematics books put it like an expansion in as something plus 1 by 1 over z, 1 over z squared, 1 over z cubed. We will get to that version of it in a while, but the z minus powers mean something very specific in the discrete time world, and we will see why we like to retain it in z minus 1. But at certain points in time when we manipulate in the z transform, it might be easier to manipulate it with positive indices in terms of instead of negative. But just remember, z to the power minus 1 is 1 over z. There's nothing unusual in that, okay? Right. So back to the question here. So if this was x kt, right? So this is t equal to 0, this is t equal to 1, this is t equal to 2. All right? You're assuming that we're starting at t equal to 0. So the first value would be 1 plus z minus 1 by 9, which is 9z minus 1, minus 8z minus 2. And so you keep going on. Right? What was the question, Sadie? I think, what did you ask? Let me see what the chart said. Yeah, 9z minus 1. Didn't I have that before? Oh, no, not t. No, the t is not part of it. Right, yeah, see what you're getting at. No, the t is not, remember the t is understood, right? So when you're given an xkt, the t is really understood inside of here, okay? So xt equal to 9, right, okay. Here we go. So at this point, let me just, what we have here, let me try to find space on this crowded screen here. xkt is equal to 1, 9 minus 8, right? K, we're starting k from 0. So this is k, this is a time naught, this is a time 1t, and this is a time 2t, right? And then if it had other values, it would be 3. So we are assuming that the first value here is where t equal to 0 is, okay? Sometimes you may get an expression, and you get numbers, and they will tell you that k is running from so and so to so and so, right? And that is where you'll have to look into it, right? But if you're not told anything, then the assumption is that the very first value in a sequence of values that you're given is t equal to 0, right? Or k equal to 0, not t equal to 0, k equal to 0, so 0t, which is times 0 at the origin, yeah? Right. So, and then this is just for information's sake. Notice all of this is just saying that this sum, this is an infinite sum. Okay? Your summing is something plus something plus something plus something. And if you remember from your add maths or your K-parts and so on, when you're given us a series of numbers, there may or may not be something called a sum to infinity. Right? The Z transform only exists if the particular thing that you're trying to find this Z transform of has a sum to infinity. Now, there are certain things that we know, like positive exponents, like e to the plus 3t, for instance. If you can sample that and you have e to the plus 3nt or kt, as n goes increases, this thing is going to get bigger and bigger and bigger as you go down the road. So this is not going to sum to any final number, right? So there are things like that. There are sequences like that, and there would be values for xkt that will not eventually sum to infinity, and therefore it does not have a Z transform. The beauty about dealing with discrete time systems, however, and it's not so much part here, but you will meet it later on if you do things like discrete signal processing, is that if something is not summing to infinity, you can basically pick the values out of it. So let's say xkt has 1,000 values, right? And numbers 0 to 900, right? Or if you want 0 to 899, the first 900 values will converge, but values 900 to 1,000 behaving like this exponent that we have here, you can actually decide, okay, I will only use the first 900 values in it, right? So you basically take a subset of the data or the values and you use it, and you will meet that later on. So that's a good thing about working with numbers, that you can kind of pick and choose under certain conditions what you want, right? So let's see how this thing applies to some things, some signals that we know, the usual approach. So the first and most basic signal that we have is, of course, a unit pulse, which is the discrete time equivalent of the unit impulse in the continuous time domain. It is not a sampled version. We made that point before. It is the equivalent to it. And what does this say is that xkt is 1 for k equal to 0 and 0 everywhere else. So it's just a single value, 1. So what is the Z transform of that? You put it into the Z transform function, and it will be only one value, which is 1 by Z to the 0, which is 1. All right? And we will talk about this in a little while, the region of convergence. This is a single value. So xz is not a series anymore, it's just a single value. So in other words, this Z transform will converge regardless of the values of Z. Z only has one value, so it's kind of a non-statement in a way, right? But we'll talk about that region of convergence in a very short while. Okay, so the Z transform of a unit pulse is 1. What was the Laplace transform of a unit pulse, of an impulse? What was the Laplace transform of delta t? 1. Not one question, 1. You should know that by now. And what was the Fourier transform of the of delta t? Also 1. Not yet, I think, perhaps. Right? So all three transforms, funnily, well, maybe not funnily enough, but intentionally, that the primary signal that we deal with, which is either the unit impulse in continuous time or the unit pulse in discrete time, the transforms that transform them to various places, the transform produces the same answer, 1. So when you go into the S plane or the S domain, you get a 1. When you go into the j omega domain, you get 1. When you go into the Z domain, right, which is where the Z transform sends you, the transform is 1. Okay, so that should tell you that there's some kind of relationship in there. How about this one? Right, we have xkt is 1 once k is bigger than 0. In other words, when k is 0, 1, 2, 3, 4, it is a series of values. And when k is less than 0, it is 0 all the time. So this is our discrete time unit step. The discrete time unit step, just a series of 1s every t interval. So what is the Z transform for that? This one again by inspection. So xkt is 1, 1, 1, 1, 1, 1, going on and on. So by inspection, the first thing, remember we're starting here, this is k equal to 0, so it will be 1 by Z to the power 0 plus 1 by Z to the power 1, minus 1, sorry, plus 1 by Z to the power minus 2, etc., etc. Right? So it's 1 plus Z minus 1 plus Z minus 2, going on and on. Right? And here's where we apply a little bit of something that we know from before, something called a GP. Right? If you have a GP and the common ratio here, right, the common ratio in here is Z minus 1, right? Oops, Z to the power minus 1, right? What is the sum to infinity of sum of infinite terms, or the sum to infinity of a GP? You remember it is given by A over 1 minus R A is the first term in the GP. R is, of course, the common ratio. And then there's one other little stipulation for that to happen. You remember what it was? That is sum to infinity of a geometric progression, right? That the common ratio had to be less than 1, right? So not only that, so A over 1 minus R, but the common ratio is going to be less than 1. So, and we'll get to that, yes, right? So if you go here, you're seeing that if we apply it to what we have here, that that 1 plus z minus 1 plus z minus 2 plus etc., the sum to infinity of that is 1 over 1 minus z to the minus 1. But that only holds if the common ratio is less than 1. And as Zidane pointed out, because z is a complex number, we really, the correct way, and I guess the correct way in most situations as well, is really that the modulus of the common ratio or the magnitude of the common ratio should be less than 1. Right? So this will converge only if mod z is less than 1. You can also flip this around and express it in positive numbers. So if I turn this around, and you know how to do that already, if I were to take this and multiply this by z over z, yeah, then what I'm going to get here, if I multiply this by z over z, I'm going to get z over z minus 1, yeah? So I could very easily convert from negative to positive indices. You know that already. You just have to look what is the largest negative number that you have here and multiply by z to the power of that, the positive power of that. So you can express this in this form. And this will only converge if mod z is greater than 1. Now they like the other transforms, the Laplace transform we drew on something called the S-plane, right? The Fourier transform, we didn't really draw it on any plane, because the Fourier transform, we were more interested on the spectrum, which was kind of one line and a magnitude. The Z transform we draw on something now called the Z-plane, right? And the Z-plane, of course, has real and imaginary parts, but they use, because they're dealing with polar coordinates, because they're dealing with Z as a complex number, in this case, they tend to use polar coordinates. When we did the Laplace transform, we use Cartesian, and we call one axis, we have the real axis and the imaginary axis, right? But there is a polar version of this, right? And you will meet that in ECNG 2009 in controls. There's some control theory that you're going to meet, and it's far more convenient if you express the instead of a real and imaginary part, a plus jb, you take it as a magnitude and an angle, and it works out far better. So in the case of the Z-plane, right, if you look at it, mod z equal to 1 is a circle of radius 1. Remember, there's a complex number, so what you're saying is that a squared plus b squared, b squared equal to 1. Well, of course, the root equal to 1, so square up everybody. That is a circle of radius 1, right, which is that red line inside of here. So, and in fact, that particular line in the Z-plane, they refer to as a unit circle, fancy name for a circle whose radius is 1. Of course, and you're expressing it in polar coordinates. So this particular thing, if you're saying that the Z transform of the unit step is only going to converge when mod Z is greater than 1, it means that that Z transform is only going to converge, or in other words, the Z transform is only going to exist in the blue range, the blue shaded portion outside of the unit circle. right? In other words, the unit step does not have a Z transform in this place here, right? Does not exist inside of it, only exists outside of the unit circle. Yeah? And we could kind of compare that to the Laplace transform. Remember the Laplace transform, we didn't do it here, but I think you did it in your math class, that the Laplace transform of the continuous time unit step, if you plot it on the S-plane, it converges on the right-hand side of the S-plane, right? Remember, this has a real and an imaginary part, and the only way that the thing could convert is if the real convert, sorry, is if the real part as t goes to infinity gets smaller and smaller. And that was on the right-hand side of the S-plane. The discrete time unit step is converging outside of the unit circle, right? So the sort of comparison, if you like, with the S-plane is that the right-hand side of the S-plane corresponds to the outside of the unit circle in the Z-plane. And remember what we said about stability? When we were talking about stability in the discrete, sorry, in the continuous time domain, for a system to be stable, the poles have to be where? The right-hand side of the S-plane or the left-hand side? For something to be stable, right, these poles have to be in the left-hand side. And actually, as Zidane pointed out, strictly left. So for the poles to be stable in the continuous time domain, for the system to be stable in the continuous time domain, the poles have to be in the left-hand side. And therefore, if you're looking at a sort of mapping, if the right-hand side of the S-plane maps to the outside of the unit circle, then the left-hand side of the S-plane is going to map inside of the unit circle. So in other words, for a discrete time system to be stable, right, when we talk about that, and we'll have poles and zeros when we talking about that, for it to be stable, the poles and zeros have to be inside of the unit circle. All right? So that's this slide here, right? So if you're comparing it, and not here, but when you're doing certain types of controls, or if you're doing discrete signal processing and so on, there are ways to take a continuous time system, and if you sample it and you get into the discrete time system and you're doing the work, you have to ensure that when you take the system, if the system in the continuous time domain had all its poles nicely located on the left-hand side of the S-plane, that when you in fact do the conversion from continuous time to discrete, that the poles land up inside of the unit circle. It doesn't happen always, okay? So what about this one now? Let's say x is some a to the power k. All right, well, we do the same thing as before. So if x is a to the power k, right, the values will be a to the naught, which is 1, then a squared, then a cubed, and so on. So the z transform of that will be 1 plus az minus 1 plus a squared z minus 2, etc. Right? Again, what is the sum to infinity of that? The sum to infinity is going to be 1 over 1 minus a z minus 1. Of course, the constraint now is that mod az minus 1 has to be less than 1. Or if you convert it into the positive index form, and you can do that, as I said, you just multiply that by z over z. And in this case, this will only converge if mod z is greater than a. All right, so you look at it here, mod z greater than a, mod z equal to a is a circle of radius a. All right, so that's mod z equal to a. This is the unit circle here. So this particular Z transform, the Z transform of a to the power k, an exponent, is either this version or 1 over 1 minus a z minus 1, either version, but it exists from this point mod z greater than k all out. It will converge, right? It will not converge inside here. And if you want to figure out why it wouldn't converge, remember how we got this in the first place. This is a sum to infinity of a GP. The only way it will sum to infinity is if the common ratio is less than 1. And when you apply that to this sequence here, it's a sequence, here is a complex number sequence, the common ratio less than 1 defines these circles beyond which the conversion will take place. Make sense? Everyone following? All right, so far no integration or anything, right? Not getting the last part. Okay, which part? Be specific. You're understanding the circle and the common way. Okay, fine. All right. Okay. Remember, well, we could go back to the unit step right here. Right? Remember that the sequence here, for instance, was 1 plus z minus 1 plus z minus 2 plus z minus 3 plus, and we're going on to z huge powers. Okay, we could leave it like that, or we could try to find a closed form solution for that. This is a geometric progression, a GP, and it has a common ratio of z minus 1. And you know from the math that this will only converge, in other words, this whole sequence of things here will have a closed form answer only if the common ratio is less than 1. If it is not, then you have the normal solution for the GP, but that's not going to help us inside of here, right? A over 1 minus n to the r, r to the n, all that kind of thing, right? So the closed form solution for this will converge if the common ratio of this sequence is less than 1. You understand that part? That made sense? Right. You understand the part about the unit circle, that this is in fact a circle. Or that if I were to write it this way, that mod z equal to 1, if I were to plot that in polar coordinates, that defines a circle of radius 1. You understand that? Okay. What's this is some a plus jb. What's the magnitude of a complex number? Is a squared plus b squared the square root of that. That's how you get the magnitude of it, right? Which is equal to 1. So I can square everything. A squared plus b squared equal to 1. A squared plus b squared, if I plot a graph, and this is my a axis and my b axis here. If I plot a squared plus b squared, I'm going to get a circle being defined here. And the radius of that, a squared plus b squared, the locus of that is a line of a circle of radius 1. So back there, so mod z equal to 1 is a circle of radius 1. And in our case, we call that, of course, a unit circle. So mod z equal to 1 is a unit circle. So if I'm saying that the z transform this now, which is the positive index version of what we just did, that the region of convergence is from mod z greater than 1, it means that if this is a circle of radius 1, right, it will converge outside. Good. And then if we go and we expand it now and we find the z transform of something looking like this now, right, which is 1 minus AZ minus 1. The common ratio here is AZ minus 1, right? So R equal to AZ minus 1, AZ to the power minus 1. So the only way that that will converge is if this is less than 1, right? So we back to that. Mod AZ minus 1 equal to 1 is a circle of radius A, right? Just flip it around. What you're saying is a Z over A, sorry, A over Z equal to 1. Therefore, if you flip it around, Z has to be equal to A, right? So that's a circle of radius A now. Mod AZ less than, mod AZ to the minus 1 equal to 1 is a circle of radius A. So if I were to plot that on the same S-plane that I had, this is a circle of radius A, so that this will converge outside of that circle, right? Inside here, mod Z is less than A. In other words, the common ratio here is less than 1. So this cannot converge because of normal GP behavior. Clear now? All right. So let's take this a little bit further now. All right, just like these slides. Right, so we look at some of the properties of the Z transform for here. We wouldn't have a long class today, but because I want you to at least follow what we're doing. So the Z transform, like the Laplace transform, like the Fourier transform, there's a table of properties for them. And many of the properties are broadly similar to what we have in the Laplace transform. For instance, if you were to zoom in on the scaling one here, all right? If you scale the sequence, the Z transform is that. You remember you had a similar one for the Laplace transform. If you multiplied xt by an exponent, that you had a scaling of the Laplace transform. So it's the same sort of thing, right? The convolution property, right? In fact, we started off using this to prove the continuous time convolution, if you recall. We didn't talk at all about the Z transform, but we spoke about discrete time convolution in a bit. This one is what we're going to pay particular attention to, and leading to one of the important properties or the useful property for the Z transform in helping us. Remember, we're doing this because it's going to help us to use difference equations, right, to solve difference equations or to manipulate the difference equations. So like how in the Laplace domain, we use the Laplace transform to solve a differential equation, but then we realized, but wait a minute, if the differential equation was describing the system, we could sort of stick into the S-plane and do a lot of manipulation right there and see how the thing is working. And this is where we came up with all these things about the locations of poles and zeros, or if the thing is stable or not, or if what do you call it? You could look at things like the final values, the initial values, and all of that without ever having to solve the thing in time. So you could get a big picture, and it's the same sort of thing here. You have a difference equation. Eventually, you have to solve it. But while you are in the Z domain, in this other universe, you could look at some of the properties there and see if how the system is behaving. So you could do all the things that we spoke about. We're not going to spend the time to do it here, but the approach, you could look for a step response, you could look for an impulse response, all right? You could look at things like where the poles and zeros are located, and we will talk about that one, yeah? So let's look at some of these properties and see if we can understand how it comes about or how they come about. So two major things in order for us to use this transform for our purposes. We need, first off, this property that if I have, first off, if I have a sequence of numbers, all right, so I have, again, my sequence 1, 9, minus 8. I think those were the three values that we had. If I delay this, remember this is t equal to, at this point, this is 0, right? So if I delay this by, let's say, 2 time periods. So instead of that, what I have is nothing, nothing, and then after the second time period, I have 1, 9, and minus 8. Yeah? Right? So this is now, if I delay it by 2 periods, this is t equal to 0, this is t equal to 1, this is t equal to 2 now. Right? Or if you want 0, t, 2t, 3t, 4t, etc. Right? That the Z transform of that, well, in this case, that the Z transform of that is just simply Zn by Xz. I have a little bit here. What is that? What is that little thing? Let me put it on the fun color. What is this underlined in red? Yeah, but the actual thing, UKT minus NT, right? A discrete time unit step. And what is it? That minus capital NT is what? Telling me what? Right? Shift how? Is that a delay or an advance? In other words, a shift to the left or a shift to the right? To the right. Good. Right, so that is, this now is a unit, a discrete time unit step that has also been delayed by some value in nt, right? So let's say, as we have x kt here. This is, the bottom here is x kt minus 2t, right? And by multiplying it by ukt, remember that would now be 0, 0, 1, 1, 1. So in other words, what I have is correct here, right? I didn't really need that, but I'm just trying to be complete. Everybody following? So what is this transform of that? Is the transform of this here, what is in blue, will be 0 by z to the naught plus 0 by z to the power minus 1 plus 1 by z to the power minus 2 plus 9 by z to the power minus 3 minus 8 by z to the power minus 4. Yeah? And what was this transform of the original thing? It was 1 plus 9z minus 1 minus 8z minus 2. Yeah? Yeah, no, maybe. Right. So notice the difference. This one is z minus 2 plus 9z to the power minus 3 minus 8z to the minus 4. The original one was 1 plus 9z to the minus 1 minus 8z to the minus 2. In other words, the new answer is this on top here multiplied by z to the minus 2, which is what this is actually saying. All right, so let me clear all this mess here. So in other words, right, we had our original, this gave us an xz, our first example, we delayed it by minus 2t, and we just showed that the z transform of that is the same xz that we had before, but you have to multiply it by z to the minus 2 into the original xz, which was z to the minus 2 into 1 plus 9z minus 1 minus 8z minus 2. Now, when you do that, you're getting z minus 2 plus 9z to the power minus 3 minus 8z to the power minus 4. Yeah? So we sort of proved it by, we proved it by an actual example, just showing it. Right, so let's forget the second one for the time being. We'll come back to that. So if I were to put it here, the first property, right? We're trying to prove this now in a general form, right? So if we just showed that it actually is so, but let's keep it general now. So we have this xkt ukt minus nt. Somebody said when you multiply a signal by a unit step, of course, you're making it causal. That's the first thing. And then this is now a delayed unit step. So first of the unit step made xkt causal. So if xkt had, apart from our values of 1 minus 9, 9 and 9, 1, 9 and minus 8, and this was t equal to 0, let's say we had a 4 and a 7. So at t equal to minus 1 and t equal to minus 2, we had some other values, right? Once a signal is causal, this is all we're interested in. To make the signal causal, we could take the whole group of values, and if we multiplied it by a unit step, it would only pick out the ones that started at t equal to 0. All right, so this is making it causal, and then as Sadie said, this is a right shift. Right, or more properly, we should call it a delay. Right, because we've delayed it, and by putting it forward in time, it is now happening at a later stage. So we've delayed it. So if we look at the actual thing now, say yz, so yz is equal to ykt is equal to this whole thing. Yz is of course xkt, right, multiplied by z to the minus k. And we could look at it graphically and see what happens. We know first off, we just explained it, that xkt multiplied by ukt, ukt is the red lines here, right? I actually had this on our PowerPoint where it was animated, but we don't have that luck today, right? So that is xkt are the red, ukt is the blue. So if I multiply xkt by ukt, it's going to get rid of all of this thing here, right? So it's going to get rid of all of that. So all we're going to be left with are these values here. And as we saw, xkt, if I shift this by some arbitrary amount, we did an example where we shifted it by 2, but if I shift the whole kit and caboodle by some amount n, right? So n could be, let's say, n50. Then at n equal to 50, now the whole thing starts. So this will now be the sequence starting at n equal to 50. This will be 51, 52, etc., etc. Both delayed by the same time. Right? We did that sort of graphically. So if I want to solve this now, what I could do is to change, to make this look more like what we want. You remember? The Z transform is the sum from 0 to infinity of x kt z to the minus k, all right? K equal 0 to infinity here. So I want this to look kind of like that. So what I'm going to do, let me change the index of summation. So I'm going to let m be k minus n. Remember this, always remember this is a shorthand. This is the same as mt is equal to kt minus nt. Remember the t is always understood, yeah? All right? So if I do that, then I have xm, I have um, which is starting to look like what I have here. And then instead of z, now I have to change the z, the summation index here. Instead of minus k is going to be minus m plus n, because I'm making a change here. K is now m plus n here. And then, of course, I'm going to have to change my indices. So this is just like when you're doing integration and you change the variable. That's all I'm doing, all right? But notice u is a unit step. So that if um is a unit step, then m could sum from 0. Because we don't have minus n values in here. So the lower limit will remain at 0. The upper limit is here. So we xm z minus m plus n. And remember, this is z minus m by z minus n. Yeah? Same thing. I just this is this. Z to the power minus n is not a function of any of these things. It's not a function of the summing variable. So I can take that out. So in other words, that by taking it out, I know I'm left with the same Z transform. Instead of defining it in terms of K, I've just defined it in terms of M. So I'm back to where I want. So in other words, if I take, and we showed it with the little values that we had, if I take a signal, a set of values, discrete values, multiplied by a unit step, making it causal, right? That is 1. And then 2, we delay the entire group by some amount minus nt, right? Or the t is understood minus n. Then the Z transform of the delayed is the same as the original Z transform, but you have to multiply it by Z to the minus n. This is why I told you that it's so important, or it's preferred for us to keep the negative index. This, remember, the minus n is a delay for us. Delays translate into a z to the minus something. The z to the minus power, in this case a z to the minus n. So whenever you see in a discrete time expression, you see something like z to the minus 3 plus 15, z to the minus 4, etc. These represent whatever values are associated with them. This represents a delay of some sort. It's telling you, in other words, where the value was in the whole sequence of numbers. Right? So like going back to that thing that we had, 1, 9, minus 8, where we started. This is not, this is time 1, this is 2 times 1. And this gave me a Z transform of 1 plus 9 Z minus 1 minus 8 Z minus 2. Notice that this one, if I were to plot this on a little graph, it would be 1. You would have 1, then you would have 9, and then you would have had minus 8. Right? This one is at time t, this is at 2t. In other words, this value is delayed relative to the first one. It's coming 2 time periods after. Hence is z to the minus 2. Right? Putting it as 8 over z squared doesn't tell the same story. Okay, so we kind of like to hold it in this form for our purposes. Yeah? Everybody following? Right. So let's see if we could get through this one now. What about if the signal is delayed by one sample? So here, I'm specifically saying that we have a non-causal signal. So I have, let's start with our favorite value since we like using that. We have 1, 9, minus 8. And let's add a few values before. Let's add 5 and 3. Right? So this is my xkt. This is t equal to 0. Right? So it is not causal. So what about if I, what is the Z transform of this? Well, the one-sided Z transform, remember, k equal to naught to infinity. So if I put this and run the Z transform for it, I am going to get the Z transform that we had before, which is 1 plus 9Z minus 1 minus 8Z minus 2. Yeah? If I delay this by 1, then time 0 now has moved, and I'll put that just so I don't erase everything. Sorry, what's that? Well, let's see. Let's see what happens. If I delay that by 1, then time 0 has moved to here. Right? So in other words, xkt minus t now has 5 included in it. So in other words, I have, if I were to take the Z transform of this whole thing as shifted, the Z transform originally is 1, 9 and minus 8. If I shift this 1 down, right, forget the first part, then you have, remember from what we said, we have the 1 plus the 9z minus 1 minus the 8z minus 2. But we delayed this by 1, so we have to multiply all of this by z to the minus 1. Right? And so that takes care of this, but we now have this value here that we didn't take into account before. So this was the point, this was the value x minus t. Originally, this was x naught, this was x t, and so on. So if I delete it by 1, I now have x minus t into it. So the Z transform of this, if it is not causal, is this plus x minus t. I have to bring him into it because he's now of the first value. Right? Let's watch graphically how that looks. Right? So xkt gives me xz, which is that bit in the blue box. Xkt minus t means that the blue box has been delayed by 1. And we just show that property. If you delay everybody by 1, then all you do is that you take the original Z transform, and the delay factor is Z minus 1. So it's Z minus 1 by xz. But because we shifted them, we have this value now that is now part and parcel of the mix. So that now becomes the first value of our sequence, which is z to the power naught by x minus 1. Yeah? Make sense? Following? I want you to follow it graphically, and then we'll go back to the math. Right? This one is fairly is easy in a way because we could shift numbers around. What about if I shifted it by 2 now? If I shifted it by 2 samples, then this was the original Z transform, the blocks that we had before, the blue block. And I have these 2 other values, x minus 1 and x minus 2. They weren't not included before. So if I shift the entire sequence by 2, the red box is now the set of numbers to form the Z transform. We already know the blue part has been delayed by 2 now. So the Z transform is Z minus 2 by the original number. And then we plus x minus 1, which is at now t. So it's x minus 1 by Z minus 1. And the next one, which is at the origin, is x minus 2 by z to the power 0. And if I shifted it by 3, and this other value here came in, it would have been z minus 3xz plus this would have gone down the road, so it would have been z minus 2 now, x1, x minus 1, sorry. This value would have been shifted down 1, so it would have been plus z minus 1, x minus 2. And then x minus 3 now comes in. So x minus 3 z to the power no. Right, so every time we shift, we have to bring in another value, and the other ones get delayed down. But the original answer, we don't have to keep working over that part in blue. That part in blue, as it goes down the road, if I were to shift this by minus 100, then this bit here in blue will be z to the minus 100 xz. But the 100 other values on this side that came in would have had a z to the minus 99 by the first one, a z to the minus 98 by the second one, a z to the minus 97, etc., etc., until we get the remaining 100 pieces that came in because of that shift. Yeah? Make sense? Just a graphical approach. Just think about it graphically. So in terms, if we generalize it, then in the general form of things, this is what it comes out to. I could delay by any amount, right? The original, once I know what the original x nt was, then no matter how I delay that, I just multiply that by z to the power, whatever is the delay. But then I have to add in all the other values that came in afterwards. This is kind of like, now notice this. What happened with the Laplace transform when we did derivatives? You remember the first derivative, dy dt. If you transfer that, you got a sys, right? And what did you have? Minus y0. Remember that? And then d2y dt squared give me an s squared y s minus y prime what do you call it? Y prime 0 minus what it is? Y what have been the y0 here, right? Something like that. Sorry, sy prime 0 minus y0, right? So you kept is a similar sort of approach taking here, that as you remember, this is continuous time, this is discrete time or difference, right? So it's kind of like bringing in the initial conditions into the situation. All right, and all you have to do is to remember, if you go back to the situation here, just remember, if I start off with a group of values and I have some other waiting here, if I shift this group down, every time I shift, I have to bring in the other values here. And each of these, just by its own, as soon as it crosses 0, starts to have a Z transform of its own. And you just simply add it to the other one that you had before. Yeah? Make sense? Yeah? Let me see what we have here to do. Okay, just a couple of slides here and we could sort of wrap up. So let's forget this is the general form of a difference equation. When you have a whole set of values, remember this is the current input, the current output, past outputs, and the current sets of inputs. right? Let's just generalize a little bit and just let n equal to 1 and m equal to n. So this is now our first order difference equation. So a general first order difference equation has one, if you like, one difference in y. You have y, you have x, and you have one order difference in xkt. Because we are dealing with LTI systems, and we spoke about this before, remember this is just a series of numbers. I could delay everybody by one time period. So in other words, if I delay this, in other words, delayed means apply a minus t to everybody onto this, then this becomes ykt, this becomes kt minus t, xkt minus t, and this just becomes xkt. All right? I haven't done anything. This is just existing in time. It's a because it's time invariant. That is the important part. Time invariant. It doesn't matter when I start my t. Okay, once I start my t, if I started my t today on started Friday, I'm supposed to get the same result. Right? Now, if I look at this now, and straight off, I apply the Z transform to it. Remember, if I take the Z transform of this, just by inspection, this gives me immediately Z, YZ. YKT delayed by 1 is going to give me Z minus 1 YZ plus Y minus T. Remember, we just looked at that, right? That was this little bit here. All right, the very first slide that we had. All right, this is something, if I delay it by 1, then I have the original transform delayed by 1 plus this value here that I have to cater into, cater for. Right? So straight by inspection. So therefore, y kt is that? Y kt minus t now is, of course, this now is going to give me z minus 1 y kt. All right, let's take the A0 here, this bit here, plus y minus t by z to the power naught. Similar for this, and this is just going to give me x z here. Sorry, what am I talking? Y z. So if I put that here, so this gives me yz, this gives me z to the minus 1 yz, minus a y kt. This here is z to the minus 1 xz plus x minus t. Remember, this is really x minus t z to the power naught. And then this gives me b minus 1 z. Remember that this coefficient is multiplying the whole thing here. So you always put the brackets. If x is causal, it means that it has no values for t less than 0. So you could take out x is causal, you could take out that. All right? So in other words, and then what we do, like we did for the Laplace things, we put all the yz's on one side and we put all the xz's on the other. And if you do that, then you're going to get an expression looking just like this, which is that yz is some function of xz, and we have the coefficients here. We have the coefficients here for B1, B0, 1, and A0. And then we have something here that is associated with only the initial values of y. This is identical to what we did with the continuous time case. What we have is the output response. Just like when we did for the Laplace transform, we have the input response and we have the initial condition response. And guess what? This bit here, right? B1 plus B0 Z minus 1 over 1 plus A0 Z minus 1, Z to the power minus 1. That is our discrete time transfer function. Right? In this domain, it is a function of Z. The continuous time transfer function was a function of S. The frequency transfer function was a function of j omega. In this case, our discrete time transfer function is a function of Z to the power minus 1 or Z to the, however it works out eventually. We'll have higher powers. Yeah? Make sense? All we're doing is applying the property that we just looked at here. Let me just get that slide back. Right. Repeated application of this property. In other words, once you, right, these two things. First off, that if you take a causal signal and you delay it, then, or a causal set of, remember, it's just a set of numbers, keep stressing that, and you delay them, that the Z transform is the same as the original Z transform would have been, except it is, you have this Z to the minus however much it delays, the delay factor. And then if the sequence is not causal, then you have the non-causal values that you have to bring into the play. And that is this second property here. And once you do that, you can now, by inspection, look at a difference equation. Look at something like this, right? This one here. If you get it like this with positive indices, you could delay it to get the negative indices that you want. And then right across here now, we could look at this and immediately, just by inspection, this is YZ, this is plus A0. This has been delayed by 1. So everybody inside of here is going to be a Z minus 1 by Z plus, because it's delayed by 1, you're going to have a Y minus T in here. And then you do the same thing. This is B0, right? It's Z minus 1 because delayed by 1, X Z plus, because it's delayed, you have to bring in the X minus P here. And then B1 XZ. Right, so I could do, if I were to give you any form now, you could just simply watch it. And then the last set, of course, the last steps, like you would have done before, would be to substitute these values if you know them. Remember, they are numbers, right? You'll be given a set of numbers if the case may be. So why this might be -7, this might be +4, that kind of thing. And you substitute it, and then you put the YZs on one side and everything else on the next. And you'll end up with your transfer function and the input response, which is the transfer function, and the initial condition response. Right? So questions? It's a little unusual, but it's not difficult, right? It's if you think about it logically, it's a very straightforward application of a process, right? All you have to do is not make some algebraic mistakes, and we all do that. I do that too. So you have to be a little bit careful. But other than that, you have no integration, right? It's not like the Laplace transform or the Fourier transform. You're going to have to integrate and look up tables and remember how to integrate sine and cosine and and cos squared and sine squared and all those kind of things. This is a strict summation. And then, of course, you have Laplace Z transform tables that go by. Yes, yes, if it is an advance, because look at the property. Where's the property? Right. This is the property here. The property is written in terms of delay. So if at any point in time you have a x kt plus some nt, then what you're going to do is to delay it by that amount. You're going to delay it, in other words, multiply everybody across by a z to the minus n, delay everybody, and then you could apply the transform. Yeah? You multiply it throughout, and because it's linear time invariant, as we said, if whatever sequence of values give you something like the difference equation that we had here, right? Once that, because we're dealing with linear time invariant systems, we can very easily, without any, go from that and delay this whole thing to get it into this form. Yeah. If it wasn't, then we're in trouble. And then we have to use some other mathematics to do that kind of thing or make certain assumptions. Okay? Right, so this concludes today's lecture. I'll stop it here. Well, today's 2 lectures. We did quite a bit, right? You're still getting away a little bit early. So when we meet next week, we have technically 2 classes, which is Monday and Tuesday afternoon formally. We have one more lecture on the Z transform to do, which would be, of course, this is now telling us, this part today told us how to get to the Z transform stage. So how to manipulate, but of course, you need to know how to get the inverse. Right? So in the next class, we're going to talk about poles and zeros, right? And then how to get the inverse Z transform. It is going to involve exactly what you know before, which is to get the thing into a certain form and get the partial fractions on lookup tables. But it also, there's another technique that is Z transform offers that you can't do with the other ones. And we're going to look at that as well. Right? It's sort of the equivalent of like what you would do if you want to get the initial response for a system and so on. And there's a way to do that. So we'll spend some time in the next class. I'll put up a slide before once I'm organized with it. You'll get that probably by tomorrow. So you can start looking at it if you want. And that topic will conclude what we have. Yeah? Right. So I hope you were able to at least follow enough of what we said here. There were some questions and hopefully we clarified it. But remember, we'll start to accumulate sort of the things of concern that people might need some clarification on. Listen to the lecture again, watch the slides, and then let me know what may or may not be making sense. And of course, if there are any mistakes that you encountered. Yeah? All right, so that being it, I'll end the class today. Let me stop the recording. So this will be one of the bigger recordings that we had.